Good morning, everybody. Happy Monday. If you could start with some green check marks, and then we will get started. Hopefully you guys had a great weekend. I know that the schedule on the homepage wasn't up right away, so happy to see a few people here at least. I don't know if Mrs. Woods put that up yet or not. The image, for whatever reason, wasn't loading properly, so sorry. You're here now, though, which is good. So we're gonna do a little bit more on what we discussed last day, and we have class today and then again on Wednesday, but we have kind of longer blocks. Great, thank you, Taylor. We have longer blocks, so we're gonna get some stuff done. We're gonna actually finish off the Unit 10, the Earth Science stuff. And then we have 2 weeks off. And I have mentioned a few times that I'd like it if you guys finished Units 1, 2, and 3 before the break, because they will not be open after the break. We're just gonna, if you're not done the first 3 units before the break, then you're just not gonna make it through the end of the course, essentially. And it's not likely that I'll get to you very much over the break. I'm going to be having a break, and I encourage you guys to get as much done as you can before then and take 2 weeks off. What a great opportunity to spend some time with your family, friends, go outside. It's been pretty nice. Ava, I was looking at the questions for 10-2, wondering if we do question 1, if we're doing the plate tectonics assignment. I'll look at that here in a second, Ava, maybe in a few minutes. And Anna's asking when Unit 2 is due, or Unit 10, sorry, is due. We're gonna finish Unit 10 before the break. So if you're completely on track with everything we've been doing, you should be done Units 1, 2, and 3. You should be done at all of those tests as well. And you should probably be done the Module 1 exam, which is kind of the first 3 units altogether. A few people had gone through it over the weekend. I had to look at the marks this morning. They're good as always, but I looked at how long it took everyone to do it, and it was about 10 to 20 minutes for the few people who had done it. So it's not like a extremely long test. It's just more questions, 36 questions. So not meant to be difficult, just more of the same. And it didn't take very long for those people who did it. Maybe we'll jump into the Unit 10 learning guide here and see if I can help you guys out with that. I loaded the plate tectonics activity into the course. So I'll just scroll down. Plate tectonics inquiry. And when we left last day, I asked you guys to go in and have a look at it and just play around with it. And I'm hoping today, once we finish class, you'll be able to go in and actually do the assignment. So we're going to be talking about this plate tectonics stuff today, and I wanted you guys to just maybe be a little bit familiar with it before we started into it, just so you could, see if you understand things a bit better, having seen it before I talked about it. So that's there. But Ava was asking about the 10.2 learning guide questions. Let's just scroll on down to those. 10.1 practice for continental drift. So you should be done that because we've done continental drift. And we're going to get through all this plate tectonic stuff today. We're not going to get to the earthquakes, I don't think. Well, we might actually. Volcanoes. Complete the 10.1, 10.2, check your understanding. Are you talking about the virtual earthquake lab, Ava? Doing the plate tectonics assignment. Plate tectonics assignment, 10.2. I'm gonna talk about this stuff here, the virtual earthquake lab, for sure. We're gonna end up doing that probably. I might leave it with you for today so you guys can get it done for next day, or maybe we'll do it next day in class, just depends on how far I get. So we are doing 10.2 today, you're right. The virtual earthquake lab we will do, I'll talk about it in class, and I think that's probably what you're talking about. So Yeah, we'll have some time to go through that today. The plate tectonics inquiry, since we're here, there was a little simulation you could run with plate interactions, continental and oceanic continental and transform and convergent, divergent, all the plate boundaries that we were going to deal with. And then there was a Word document to go along with it. So I initially just asked you guys to go in and look at the simulation just to kind of play around with it and see what it was all about. And now I'm going to get you guys to actually do this assignment. So it's just 2 pages, not too long. And basically you just go into the simulation, you just go through the questions step by step. It's not a difficult thing. It tells you how to set everything up. It says, select these buttons or do this, do that. Describe the differences between oceanic and continental crust, predict how changes occur, predict movement based on composition of the plates. So if you're looking at what the plates look like when they come together or move apart, what's going to happen as a result. So what you do is go to the simulation. You're going to do both tabs at the top. There's 2 kind of tabs you're going to go through. The crust tab is the first set of questions here. So grab the thermometer for letter A. It says describe the temperature. So go in, drag that little thermometer around and see if the temperature goes up or down, just depending on where you are. Describe how high you are, if it's hot or cold. If you go lower, does it get hotter or colder? And what do you think causes the differences? We'll talk a bit about that today. Change the crust into oceanic crust. So you go through that. Have a look at the density. What is the density? Is it, pick the layer you're in. So was it crust? Is it something else? How does this layer's density compare to the picture? Greater than, less than, equal to. Why do you think that is? So that's the first tab, the crust tab. And then you go to the plate motion tab, which is the second one. And basically you're going to look at all of the different types of plate interactions you can have. So it's going to tell you to set it up. Like example 1 says drag an oceanic crust and a continental crust, and then move it in the direction of the green arrow. So you're bringing them together. What happens? And you're supposed to draw a little picture of it. And then what's the outcome? Does anything happen? Volcanoes, earthquakes, what happens? So you just describe it in that regard. So that's kind of the activity. You do the 3 different examples, and then you can just play around and find anything else you found interesting. So I don't think that should take very long. Does anybody have any questions about that? You can download it to your computer. You can do it on the computer, or you can do it by hand. Doesn't matter to me. And then you can submit it with your learning guide at the end of Unit 10. So just like we've been doing, I'd like it to be done for Friday. I would like all of Unit 10 to be done on Friday. So you can do that for Friday. That's the only question. I think we're doing okay. I'm going to jump into 10.2. If you guys do have anything that comes up, let me know. So plate tectonics is 10.2, and we're just going to kind of plug away through here. So this obviously matches up with your notes. Yeah, Taylor, you can print it if you want, or you can do it on the computer. I do not mind either way. I'm easy. So the first thing we're going to look at is layers of the Earth. So the Earth's about 1,200 kilometers thick from the edge to the center. So we're talking about a radius, not a diameter. Obviously double it to get the diameter. And we have these distinct layers that make up the Earth. Now, it's always interesting to think, how far have we ever gone towards the center of the Earth? So, I don't know, in chat, just throw in the furthest distance you think we've gone towards the center of the Earth in terms of not like a human, but like a drill hole. So remember, it's 1,200 kilometers to the center. Alex is going with 12 kilometers. What do you think? It's 1,200 kilometers from the edge to the middle. So 12 doesn't seem like a lot, but it's a guess, I suppose. Abby's going to just agree with Alex. Maybe you guys are just... You're on top of it, you already talked about it before, and you know exactly how far we've drilled into the center of the Earth. Haven't you guys ever watched that beautiful cinematic masterpiece with Brendan Fraser that is Journey to the Center of the Earth? Alex, you've already seen the documentary. You ruined it, man. You ruined it. Anyways, we'll talk a little bit about it. So again, I don't love memorization, but unfortunately you have to know the layers of the earth. And this isn't something that comes up in your learning guide, so you can't just refer to an image. You just need to know what they are. So you end up with the crust. That's where we live. We're on the top, we're on the crust. And then you have upper mantle, lower mantle, and inner core, outer core. So you don't need to memorize the thicknesses of each of these, but you should have a general idea of how thick they are. So the crust, in general, is between 5 and 70 kilometers thick. So we're going to talk a little bit about the lower limit and the upper limit and why those are. And then you have this upper mantle. It's about 600 kilometers thick. And then the lower mantle, 2,000, then the outer core, inner core, another 2,000, and then another 1,000. So they're pretty thick. The consistencies of these things are also important. That's what's here in the notes. So the crust is hard. It's kind of granite. This is what we walk on. So if you go and you see just rock exposed next to your house or in a rock bluff somewhere, it's generally like a granite type rock, and it's hard. And then the mantle, it has two parts to it, the upper and the lower. And the mantle is mostly solid. And then the upper mantle, we call it like a thick toothpaste, but that's not even true. It's even thicker than that. It's somewhat fluid, but it's very, very, very dense. So don't think of it like water. Think of it more like even thicker than toothpaste, kind of like almost plasticine almost. So really thick, like a clay almost, but not clay. It's hot, it's molten. It's hard to describe because we don't have anything to really, in our everyday lives, that kind of looks like it. The outer core is liquid, which is pretty cool, and we'll look at some really interesting things that happen as a result of that. So it's so hot in the core of the earth that there's this liquid outer core. So the metal, iron and nickel, at that sort of temperature, they're actually a liquid. So it's so hot down there. And then the inner core is solid iron, and there's an absolutely immense pressure and temperature down there. And we'll talk about why that is in a second. So I asked what the deepest we'd ever gone down was, and Alex knew it was 12 kilometers, which was the right answer, which is kind of amazing when you think about it. So we talked about the crust being about 5 kilometers thick in some places and then 70 kilometers thick in other places, and on average it's probably around 20 or so if you averaged it out. But this image here is in miles. It's the only one I could grab that had all these interesting things on it. So we have to kind of mentally convert all of these numbers into kilometers in our head. But over on the far side here, just kind of above my head, is the Kola well in sort of northern Russia. And they wanted to see how deep they could dig. So they started digging, and they got down to 7.6 miles, which is about 12 kilometers. And at that distance, the temperature was so hot that it started to have really negative effect on the drill bits, essentially kind of melting the drill bits. It was so hot down there, which is pretty interesting. So there's some other ones in the USA. There's another well that's about 6 miles deep, so close to 10 kilometers. The ocean crust is a lot thinner, which is interesting, and the furthest we've ever been through there is about 5,000 feet, which isn't a mile even. And then the deepest natural thing that we've ever found is a cave in France. It's about 5,000 feet deep. So there you go. Yeah, it's kind of something we take for granted. We live in this tiny little envelope on the surface of Earth. If you go up 12 kilometers, you're in space. If you go down 12 kilometers, it's so hot that you'd literally just ignite and burn. So, we don't really have a lot of area on the surface of our planet to live in. Pretty crazy when you really think about it. And we haven't really explored that much in terms of below our feet. We know a lot about, what's on the surface, but we don't know very much about what's below the surface. And there's some reasons for that. we can't just go down there. There's no easy way to get there. So anytime we want to go down there to do something, we have to drill a hole, and that is a lot of work. So we're going to talk a bit about the tectonic plates today, which is some pretty interesting stuff as comes as a result of them. So remember we talked about the crust being anywhere from 5 to 70 kilometers thick. The crust under the oceans is very thin. And that really makes sense. If the crust under the ocean was really thick, well, there wouldn't be an ocean there. You'd have a continent. So where we have continents, the crust is very thick. And where we have oceans, the crust is very thin. If the crust were any thicker, then you'd have a continent. So that kind of makes sense when you think about it. There's two more words, lithosphere and asthenosphere, which are written over on the side here. And this is where the layers of the Earth gets really confusing. So far we had the crust, and we had the upper mantle, lower mantle, outer core, inner core. That all made sense. You're like, got the crust, perfect. Outer mantle, inner mantle, or upper and lower, I should say, and then outer core, inner core. That's good, perfect. Then we get these ideas of lithosphere and the asthenosphere. And there's something that happens at the upper mantle. The upper mantle isn't the same consistency from all the way from the bottom to the top. The upper mantle is actually broken into kind of two parts. So the lithosphere is the crust, so any continental crust or oceanic crust. And then the very top part of the upper mantle here is solid. It's kind of like what we consider the crust to be, so kind of like rock-like. So you can see this top portion of the upper mantle, about 70 kilometers or so, the upper mantle is this kind of hard stuff. And then you get this, it's called the MOHO discontinuity. So a distinct line exists in the middle of the upper mantle or somewhere near the top of the upper mantle where you get this break, and it goes from being a solid, kind of like a rock in this lithosphere part here, and then you get kind of a molten layer down here. So the lithosphere is kind of like a boat, and then the asthenosphere is kind of like the water that it floats on, but it's not really water. So when we talk about the layers of the Earth, it gets really confusing, and I rightly get confused because you have these layers, and then you have this upper mantle, and the upper mantle is actually broken into two parts, the lithosphere and the asthenosphere. So the lithosphere is kind of like the boat that everything kind of is floating on the asthenosphere, which is down a bit lower. I'm so glad you asked that question, Alex. How do we know what this looks like if we can't go down there? So remember we've gone down 12 kilometers, so like we're right here. This is how far we've gone. Barely even scratched the surface. We've never been there, but we can take indirect measurements. And this is how we find out so much about science. We propose a theory, we test it, and then if it, becomes true, or if the results support what our hypothesis, then we call it a theory. Now, we have no way of knowing for sure, but we have developed the scientific method. We propose a hypothesis, we test it. If it becomes true, it becomes a theory, until we can prove it with certainty, and then it becomes kind of like a law of nature, if you will. So we do lots of indirect measurements. We'll look at how we can use earthquakes to help us figure out what's down there. We can set off explosions, and basically the waves will travel down and then they'll bounce back up, and we can see what happens as a result of those. There's lots of really indirect ways we can use to measure, but the truth of it is we just don't know for sure. And that's why in science we have lots of different theories about how things work, which are supported by evidence. And until we can verify for sure, it just stays as a theory. So this is science, right? Science in general. Okay, so the asthenosphere is this molten layer that everything kind of floats on. It's like magma as you think of it. And then basically there's all this heat in the upper mantle. And that heat is a result of radioactive elements. So we're going to talk a bit about radiation after the chemistry unit, but this radiation, it creates heat. If you think about nuclear power, that is heat that we're using. We're trapping that heat and creating energy out of it. Same idea here. We're using this heat caused by all these radioactive elements that exist down there, keeps everything liquidy. So, Abby, you're talking about the new gravitational waves that we just discovered a couple weeks ago, which is exactly what I'm talking about. Einstein, almost 100 years ago now, he proposed this idea of gravitational waves. He said these waves exist, here's the math to prove it, and it became a theory. And people are like, well, yeah, it's a good way of describing how things work, and wouldn't it be cool if we could actually verify they exist? And it wasn't for almost 100 years later, we now have the technology where we can do these really intricate, highly detailed experiments where we have these essentially evacuated tubes under the ground that are kilometers long, that have interferometers in them, which are basically laser beams bouncing off mirrors, and the gravitational waves kind of disrupt those laser beams a little bit, and they cause an interference type pattern, and we can prove that these gravitational waves exist. We've only ever seen it happen once. There's a couple black holes that were kind of orbiting each other, creating these gravitational waves that were so strong that they made it to us. And yeah, so that's exactly what we're talking about. We now have the technology to prove it. And maybe we don't have the technology right now to drill down into the earth to figure out what's there, but we have theories, and we'll support those theories with what we can until we have the technology to create evidence to make them no longer theories. So, we talked a little bit about this when we were dealing with the Mid-Atlantic Ridge. So we looked at those pictures of Iceland where the actual continents were being pushed apart. And this is actually what's happening kind of under the ground. So we'll take a little look under the ground. You have these tectonic plates. So you have this lithosphere kind of floating on the asthenosphere, and they're kind of floating around, and you get these big plumes of magma pushing up, and they rise up and they start to kind of crack the surface. They crack the plates a little bit, and the plates start to get pushed apart. So you can see this happening here in kind of steps. You get this big rising plume of magma, convection current, and it starts breaking through. So these are like volcanoes. Remember, this is on a really large scale. And as they get pushed farther and farther apart, you end up sometimes with a valley here, or all the time. And then as that valley forms, water will fill it in. So it becomes like a lake or an ocean. And then as they get pushed further and further apart, you get ocean. And these plates are constantly moving apart, and new magma is filling in the void here. And it's creating oceanic crust in the middle of the continent. So this is exactly what happened between North America and Africa, and South America and Africa. You had this big rising plume of magma pushing these plates apart, and it's called ridge push. The plates are constantly slowly getting pushed apart by the magma in the middle, and there's constant new oceanic crust being formed between them. So that's exactly why you end up with underwater volcanoes. There's some other reasons, but this is the main cause of that. So we call it ridge push. You get a ridge in the middle because all this magma is pushing it up. So even though they're separating, they're getting spread apart, because there's so much magma pushing up, they kind of have a little kind of ridge in the middle. And the water gets there from rain, or the valley could open up so far that an ocean can start to fill it in because it's lower than sea level. Remember, the continental crust is really thick. And if we start replacing that really thick crust with really thin oceanic crust, it's not oceanic crust right away, but this really thin crust, all of a sudden it's lower than this thick crust, and water starts to fill it in. Remember, these things are happening over millions of years. So yes, it is a lot of rain, but even if it rains, a meter a year over 1,000,000 years, that's 1,000,000 meters of water. What happens to it? Well, it rains, it follows kind of the lowest path to an ocean. If the Rift Valley is the lowest part, it'll fill up. If it's really hot, it'll evaporate. It just depends on where it is. So these processes take place over millions of years. We talked about the continents moving apart about 1 centimeter or 2 centimeters a year. We're talking extremely slow processes here. So very long periods of time these things are happening. So that's ridge push. There's two methods of things that cause these plates to move. So ridge push is the first one, and then the second one is slab pull. And you end up with a push, you got to have a pull. It's just how it goes. So if you think about tectonic plates, you get this big push in the middle and they start to spread apart. Well, it's moving away from the center. What happens at the other edge? You have these big plates, so this plate's kind of moving away from the center. What happens to it? Well, it's going to bump into something over here. That's what this image is showing. The image is showing your ridge in the middle, so you have this rising plume of magma coming up, and you get this plate, oceanic plates getting formed, but this is moving constantly. Now you get this really thin oceanic crust, and it bumps into a really thick continental crust. What happens? Well, if you take something really big and you push something up to it that's really small, think about cars. If you take like a big, huge truck and you take a little smart car and they have a head-on collision, what happens? Well, the big truck just runs right over the smart car. The smart car goes underneath. And that's what's happening to the continents. So as they are getting pushed apart, the other edge on either side, it bumps into this really thick continental crust and it actually goes underneath it. And if you've ever set the table at your house and you put on a nice tablecloth, but you have like a really smooth table. I know this used to happen to me when I was a kid. And that table is really smooth. And then your tablecloth's not exactly centered. It's kind of over onto one of the sides. And then it starts to kind of fall off the edge. You know, gravity pulls it off. And then all of a sudden it just keeps tumbling and just goes whoosh right off. That's kind of what's happening with these plates. So you get the push in the middle, the ridge push, the plate gets pushed along, and then when it hits the continental crust, it dives down underneath. And once it starts to go under, it just keeps going under. It just keeps pulling the rest of the plate under. So you have kind of two things happening. You get a big push in the middle and a pull on the other edge. So these are the things that are happening when plates kind of interact. So this is what causes the plates to move. You get these big plumes, cause the push. Once it starts to go under, you get a pull. And what you get here is a subduction zone, it's called, where one plate subducts under the other one. This is called a subduction zone. And some interesting things happen at subduction zones. So this is where you end up with lots of earthquakes and volcanoes being produced. Once this slab starts to go underneath, it gets hotter and hotter, and all the friction here between this oceanic plate and this continental plate, the temperature is just immense, and it melts and basically turns back into magma, and then it rises again, and this oceanic sort of situation here just keeps kind of getting recycled. It goes, rises up, becomes solid, where it's nice and cool at the surface, you get a lot of friction, heats up, melts again, and then rises back up, solid, melts again, and it just keeps getting recycled. So that's what happens with these plates. So let's slab pull. So these are the two methods which you'll end up causing these plates to move. Ridge push, slab pull. Those are the two ways they move. The continental plates kind of just float around. They're just kind of hanging out. So this is an image of the main plate boundaries, and I like this image because it's nice color coordinated. The image from your data booklet looks a little bit different. So if you have a data booklet somewhere near you, you might want to grab it. If not, I'll just come back to the image and we can go from there. What goes into the place where the plate used to be? So that's kind of right here. You're talking in the middle of this Rift Valley. You get new magma rising up, and then it comes to the surface where it's nice and cool and it solidifies. So the plate used to be here. As this plate moves, new magma is constantly being deposited on this edge, forming new rock. So this rock's really young, and then as it gets over here, it gets older, and then it gets born again, really young, older, and you get sediments and things like that being deposited over long periods of time. So this gets back to the idea of magnetic striping that we talked about last day. As that new rock gets deposited, the magnetic north pole is pointing this way, and then it gets pushed apart, and then the poles will switch about every 100,000 years, and now the pole will be pointing the other way, and then that gets pushed apart, and then a new pole, and then pushed apart, and you just get this striping. Is it in water when it happens? Generally speaking, these rift valleys, the ridge push will happen underwater, but not always. We'll look at an example here in a second where it doesn't happen underwater. And you guys will be experts on looking at this stuff. So this is kind of the major plates. There are lots of minor plates that we don't really talk about. We're just concerned with the major ones. So you can see all of North America's major plate, South America, Africa. Off our coast here, we have this little plate. It's called the Juan de Fuca plate. And if you've ever been down to like Victoria area, it's the Juan de Fuca Strait is between Vancouver Island and the mainland. Gets its name from the plate here. There you go. Yeah, so the only one that's kind of, there's a couple of smaller ones here like Saudi Arabia and India have their own little plates. But generally speaking, the plates are pretty big. And this image here, this next one is from your data booklet. So this is kind of the one that you get on tests, and you should be able to identify what's going on. Now, at the very end of my presentation here, I say the symbols are important, but we should talk about them now. So we haven't talked about the names of these things yet: divergent boundary, convergent boundary, transform. We're going to do that in a second. But you have this, a set of labels down here, a key at the bottom of your map. And you should know what these things are. So a divergent boundary is these two lines. So in the middle of the Atlantic, you have a divergent boundary. And then a convergent boundary, these little triangles on the lines, kind of off the coast of South America here. Transform boundary is just a straight line. You end up with one kind of over here. There's some other ones right here. And then mountains and volcanoes are pretty straightforward. And there's giant arrows that show you where the plates are going, in what direction they're generally moving. And here is just another page from your data booklet, but it's just our neck of the woods sort of idea. So specific to British Columbia off our coast. So you can see that you have all these volcanoes in BC, but you think, I didn't ever think that BC was a seismically sort of significant place. But yeah, there's tons of volcanoes in BC. A lot of them are dormant, but there are a lot. If we go down towards Washington State, the Cascade Range is kind of the extension of our coast mountains up here. You've been to Vancouver, you've probably seen Mount Baker in the distance, which is really close to the border. And then we're going to talk a little about Mount St. Helens next day, our kind of active volcanoes that are, I say Mount St. Helens is more active than Baker. Baker's fairly dormant these days. But there you go. So that's our neck of the woods. There are some volcanoes really close to Vancouver, actually, which is a big deal because there's millions of people that live in the Lower Mainland, and they're very close to a dormant volcano. So we'll talk a bit about that. So the plate interactions, there's only so many things that can happen when you have two plates come in contact with one another. So they can move apart, which is divergent. They can come together, which is convergent. And they can slip past each other, which is transform. So these are the three different types of interactions you can have. It seems like, oh, there's only three, that's easy. Well, we run into problems, not problems, but you can have different plates bumping into each other. So you can have continental plate, like a real thick one, and an oceanic plate. What happens when they bump into each other, move apart, or you end up with different types of plates interacting. Ava, wasn't there a volcano in West Bank? Yeah, there's an ancient, really, really old fault line that runs down pretty much the middle of the Okanagan Valley, so under the lake. And there's a few volcanoes that are there that existed before the last ice age. So if you've ever seen Mount Boucherie, which most of you have, it's kind of a really sort of reddish dark color. That's because it's a caldera. So in the middle of a volcano, you have this big magma chamber. And that magma chamber filled up with magma, and then it cooled and became this really hard rock. And as the glaciers came through the Okanagan Valley, it scraped the top of the volcano off, and that really hard rock that was left in the caldera was left over. So Mount Bushiri is the caldera of an ancient volcano. If you look the other direction, if you look towards sort of Big White up Highway 33, Black Mountain is black. Why? Well, it's a caldera of another volcano that used to exist here as well. So a long, long time ago, our area used to be volcanically active, but we're talking long time ago. All right, let's look at the different types of plate boundaries. Divergent boundaries are where you get plates spreading apart. So on your map or on the data booklet, there'll be two lines, kind of parallel lines, and that'll show a divergent boundary. So you end up with oceanic ridges, so we call it the Mid-Atlantic Ridge. That is a rift valley that's under an ocean. If it happens on land, it's called a rift valley. So we end up with sort of two names for the same thing, depending on whether it's on land. If it's on land, it's called a rift valley. And then if it's under the ocean, it's called a ridge, an oceanic ridge, because you get this little, like a valley under the water, but because it's being pushed up with all this magma, this plume underneath, you end up with a tiny little ridge. So if you have your data booklet nearby, I can go back a couple slides to the picture. In chat, just find a place where you've located a divergent boundary. So look for the symbol. Let's use this map here for now. So the symbol for a divergent boundary is here. Where are all of the divergent boundaries on this map? Can you find a divergent boundary? Obviously, there's one down the middle of the Atlantic. We talk about that one a lot. But can you find one on land? Is there any divergent boundaries on land? Where is it? Find it. There is at least one I can think of. That's all I can think of, actually. That's all I can see as well. There's one divergent boundary on land. So you have a rift valley being formed on land. Eurasian plate. Eurasia's here. I'm not seeing one on the Eurasian plate, but right here, unless you're talking about down here, which is actually this Saudi Arabia has its own plate. And then right here in Africa, you have this rift valley, Arabian. There you go. So the Arabian plate is being kind of separated here. So right along this rift valley, you get a bunch of volcanoes in Africa because this plate is kind of being separated right now. So this is kind of the main spot in the world where you end up with a divergent boundary on land. There's actually one other spot, and we actually talked about it last day, the Mid-Atlantic Ridge. It runs right through the middle of Iceland. So if you go up here to the North Atlantic, you end up with this tiny little island of Iceland, has this, this rift valley in the middle of it, and there's tons of volcanoes on it. It's highly volcanic because you have these plates spreading apart and magma forcing its way up. So there you go. Those are your divergent boundaries. So you're looking for parallel lines. This is it's called the East African Rift Valley. So this is an actual photograph from the air of this rift valley in Africa. So you can see the two plates here, the edges are moving apart, and in the middle you end up with volcanic activity, which is kind of interesting because the volcanoes in rift valleys aren't just one volcano. Kind of, you think about like when somebody says volcano, in your mind you think of these big towering cones like Mount Fuji or Mount Baker, big rising up from the ground, huge pointy volcanoes. Well, that's not what happens at these rift valleys. You have really long distances where the plates are moving apart, and in the middle you get all of these volcanoes popping up all the way along the rift, down its entire length. So above my head here, you can see you have this huge plume underneath Africa, and it's rising up and it's pushing Africa apart. And you're ending up with this rift valley. And I think we were asking earlier, well, how does it fill with water? Well, it isn't really below sea level yet, but as these plates get separated farther and farther apart, and as this new magma gets deposited in, it's going to be very thin, and the ocean's going to eventually fill it up. So down here below, you kind of see it happening. These red lines are showing the rift valleys that are forming as a result. And in a couple million years, you're going to end up with Africa, which is right here, which would normally come up like this. It's going to end up being a big inland sea or an ocean. So as these plates get separated further and further, this red line is going to eventually fill with water, and then you're going to end up with this little piece just kind of splitting right off. So it's going to become a big island. So that's a rift valley on land. That's what it looks like. So kind of interesting. Whew, that's a lot of writing. Convergent boundaries are a little bit more varied. So when you have a divergent boundary, it's going to be underwater or it's going to be on land. And those are the only choices. Yes, Somalia will become an island millions of years from now. Interesting? Possibly? Yes. There's some evidence to suggest that it might not, but for the purposes of this class, yeah, it'll become an island. It's complicated, right? It's difficult to predict what the weather is going to be like in 5 days from now. Trying to predict what the Earth is going to look like in 100 million years from now is kind of like we use computer models to predict it, and we can look at what's happening now, and we can broadcast that into the future, but there's no guarantees. The Earth is a complex thing. These are very complex cycles, and you end up with some unknowns that we can't fill in. So we do our best to describe it, but we're not perfect. Okay, convergent boundaries. So when plates come together, divergence, easy. You have it on land, you have it under the ocean. That's it. There's the two options you have. When you have convergence, so plates coming together, there's three options. If you have a thick continental crust and a thin oceanic crust, and they come together, this is the giant Hummer running into the tiny smart car. The Hummer just goes boom right over top of the smart car. Smart car goes underneath it, and you get a subduction zone. So right behind me here, you get this subduction happening where this plate gets the slab pull underneath. And right here, all of this rock is under immense temperature and pressure. So it becomes really, really hot. What happens when things become hot? Well, they start to rise. So they rise up to the surface and they break through the surface. And this is where you get volcanoes. So instead of it just being one volcano, like Mount Fuji or Hawaii is a good example, you get really long strings of volcanoes. So this is very common all around the world where you see an oceanic plate getting pushed under a continental plate and you get a long line of volcanoes. So we'll talk a little bit about the notes here, and then I'll show you some examples of this on the map, or you guys can find them. So the oceanic plate's denser. The continental plates are kind of fluffy and light. Not really, they're made of solid rock, but oceanic crust is really dense, whereas continental crust is a lot lighter, less dense, I should say. So because it's running into it, you get subduction. It goes underneath, and that subduction zone is where you get things like volcanoes and earthquakes happening as the plate kind of slides underneath. It gets caught, and then it gets going again, and it gets caught, and then it slides again. And it's constantly happening, very slowly. So most of the mountain ranges in British Columbia are formed as a result of this exact process. So British Columbia would normally be just nice and flat, but you get things like the Rocky Mountains. The Rocky Mountains are fairly old mountain range, but they resulted because that Juan de Fuca plate, or the Pacific plate, I should say, was getting pushed underneath our nice thick North American plate. So you end up with this immense pressure and this immense temperature, and this rock starts to become liquid again, and then starts to work its way up through the surface, and you get these really long chains of volcanoes. So volcanic belts or volcanic island arcs, if you can, on your data booklet, if you have one near you, or I can just jump back here, can you find an example of a chain of islands that is as a result of a convergent boundary, an oceanic plate diving under a continental plate? Can you find an example of that in your data booklet? I know there's some examples here in the notes, but can you find it happening anywhere else? There's a couple in our neck of the woods that are fairly common. Some other famous places that are known to be volcanically active. So if I look at just our neck of the woods here, just BC, up in the north, if you guys have ever seen the show where they go fishing for crab, Deadliest Catch on Discovery Channel, this is a good example of it. So the Pacific Plate is diving under this North America plate up here, and you end up with this, yeah, Abby and Taylor, you're both right. We'll get to them in a second. You end up with this subduction zone. So these triangles is a convergent boundary, and because these plates are coming together, you end up with this oceanic plate, the Pacific Plate, diving under this continental North America plate. And what you get is the Aleutian Islands, which form this volcanic island arc. So this is called the Aleutian Trench, where you end up with this stuff happening. So that is an example of that happening up in Alaska, Bering Sea up there. If I jump back one further, so these were the examples you guys were talking about. Abby mentioned the Nazca Plate, if I can find that. We were just looking at that. Oh, here it is. Abby and Taylor both saying the same thing. So this is a perfect example of it. You have the Nazca Plate, which is being pushed here by a divergent boundary, so being pushed along, and then it's running into this really thick continental plate. It's running into South America here, and it's diving underneath it. And the mountain range that's formed here, does anyone remember what the mountain range is off the west coast of South America called? When do you learn about mountain ranges? It's got to be like grade 7 or 8. I remember having to memorize those when I was a kid. So you get these volcanic arc being created as a result. These are the Andes Mountains of South America, Chile. So that's happening there. Another example kind of happens over above me here. The Pacific Plate's also running into the Eurasian Plate, and this is why Japan is so seismically active, because you end up with this plate getting subducted under it, and you get all these volcanoes that form that created Japan. And then even down here, you have Indonesia having the same sort of thing, and the Philippines. The Indonesian islands are these, the chain is formed because of subduction happening. So there you go. Those are kind of the big, thick continental plate, the tiny oceanic plate, and they get subducted underneath. So we did that. Oceanic plate convergence. So if you have two really thin, really dense, but really thin oceanic plates, they bump into each other, what happens? Well, one wins. One will eventually go over top of the other one, and one will get subducted underneath it. So you end up with oceanic subduction happening as well. And this is where you'll get these really long chains of volcanoes, like the Aleutian Islands that we were talking about, Japan, Philippines, Indonesia, all exist because of oceanic plate convergence. So you get a volcanic island arc, and they just turn into long chains of volcanoes at the subduction zone, this big trench that gets built up here. So colder, denser plate will get subducted under it, and then you end up with long chains of volcanoes. So eventually the volcanoes will break through the surface over millions of years, and you end up with long chains of islands. So the Aleutian Islands, Japan, those are great examples of this oceanic convergence. So thick continent, thin oceanic goes under. Two oceanic plates, the denser one will subduct and you get islands formed. And then we're going to look at the last example of convergence here in a second. Notice, though, that the islands don't form right at the trench. These volcanoes or the islands actually form a little ways away because as this plate gets subducted under, this heat and magma starts to rise up, but it doesn't rise up right at the point where the plates meet. It takes a while for it to melt and rise up and ends up right here. Abby, Hawaii is actually an example of a hotspot. And we'll talk about hotspots in the second half, possibly tomorrow, not sure. See how far we get. And hotspots are really cool. I'm going to look at a couple of those, but not an example of subduction. And if I jump back to the map here, you can see Hawaii is actually in the middle of a plate. So the plate is here, and if it continued on, it would continue to the other side of the map here. But it's actually right in the very middle of the Pacific plate. And you can see a little volcano in the middle of Hawaii here. It's not at any plate boundaries. So we're not talking about any plates coming together, any plates separating apart. It's just basically a really hot spot underneath there. It's breaking through the surface. All right, so oceanic convergence, we've looked at that. The last type of convergence you can have is two continental plates coming together. Now, this doesn't happen a lot. There's only a couple spots where it does happen. But you have these two really thick continental plates. It's like two semi-trucks running into each other. Well, what happens? Well, generally speaking, one's not going to go under the other because they're just so big. They're just going to be a just big crumpled up mess. They're not going to, go under. They're just going to run into each other and make a big giant mess. So this is what happens in a few spots, and we'll try to find some examples of it. You can see there's no really distinct things going on. There's no subduction. There's no push or anything like that. They just kind of run into each other. And this is the idea. If you think about taking two rocks and you push them together, well, what's going to happen? They're rocks. They're extremely hard. They just bang into each other, and that's it. Maybe you can chip pieces off of them. But when we start talking about really, really large forces, over really long periods of time, rock will actually start to bend and fold and things like that. So you can see the layers of the rock here. This would normally just be kind of flat layers of rock. You can see them flat over here. But once they start to push into each other, it bends and folds and all sorts of crazy things happen. You get earthquakes. And we think of rock as being such a static thing that can't really move or bend or fold. It's just really hard. But the amount of energy we're talking about here is enough to make rock actually bend and fold. So pretty amazing when you think about it. The best example of this, I'm not even going to make you find it, but I guess I should make you find it. Find an example of continental convergence on your map. Are there any examples of it? It gives you the example of the Himalayas here. Does it happen anywhere else? Is there anything else going on? So when you end up with these two big, thick plates running into each other, magma doesn't ever really form because you have these really thick plates that magma can't rise up. You end up with not as much going on. So if we jump back to the image here, we're looking for convergence. So that's a line with the little triangles on it, but with two continental plates. So you're looking for the line with the triangles happening on land somewhere. So Scotia Plate is right here. So this is an oceanic plate. So this isn't continental convergence because we don't have a continental plate here. This is a nice thin oceanic plate. The only place it really happens is right here, just above my head. The Eurasia plate and India. And India is actually a bit of a smaller plate, but they've showed it as the Indo-Australian plate. But India was its own plate. And India is running into Eurasian plate right here. And this is, here's another example of it. And these are the youngest mountain ranges in the world. This is the Himalayas right here. So this is India, you have China and sort of Tibet kind of jammed in here. And this is the highest elevation above sea level. So Mount Everest is 8,848 meters above sea level. And because those plates are still moving, they're still coming together, every year Mount Everest gets a little bit taller. We're talking millimeters, but it is getting taller. So you end up with weathering, making it smaller, and it's trying to rise, and these plates are coming together, but all of those mountains in the Himalayas are actually getting taller each year as those two plates run into each other. So if you were to climb Mount Everest today and somebody else, your friend, climbed it tomorrow, they're technically climbing a taller mountain. It wouldn't be measurable, but they're technically climbing a taller mountain. So that is continental convergence, and you can see all these mountains that get formed as a result of it. And the Himalayas is the best example of that type of thing. So there's continental convergence. So the three types of convergence: you have two oceanic plates, you have a continent and an oceanic plate, or you have two continental plates. Those are the only three things that can happen. The last type of boundary we're talking about is a transform boundary. So this is, instead of plates running into each other or spreading apart, they're actually moving side by side, so they're sliding past each other. And there's a really famous example of this in kind of our area, and we'll talk about that here in a second. But transform boundaries are the result in lots of earthquakes, because these plates, they start to move, they're going in different directions, and then they'll slip, and then they'll lock up again, and energy will build and build and build, and then they'll slip. And each time you get a slip, that's what causes an earthquake. So because you have two plates sliding past each other, you're not going to get volcanoes. There's no weakness for magma to rise up. They're not spreading apart, allowing magma to rise. One's not going under, creating magma to rise. You just have these plates sliding past each other. So you get lots of earthquakes, but not very many volcanoes. And the famous example of this one is the San Andreas Fault in California. Basically runs really close to LA and San Francisco, right kind of through the heart of California. And that's why the California area is so prone to earthquakes, because you have these two plates sliding past each other. And every once in a while you get a very strong earthquake as a result. If you get lots of small earthquakes, that's a good thing. Lots of energy is being released in really small increments, perfect. When you don't have earthquakes for really long periods of time, that's when bad things are going to happen, because you're going to get a big slip and you're going to get a big earthquake. And you'll notice the symbol for this is these little arrows. So you'll get a line with two arrows going in opposite directions on either side of the line. So that is a transform boundary. Let's look at an example. Well, here's an image. This is the actual San Andreas Fault here. You can see running down the middle of this picture. And this one plate here is going down. This plate here is going up. And it's a physical line, which you can actually see from the sky, which forms this boundary between two plates going in two different directions. So there you go, transform boundaries. They are just a line with arrows on either side of it. I guess it's worthwhile to just jump back to our main sort of map. This is our neck of the woods here, the Juan de Fuca plate. You can see a transform boundary right here. You have your two arrows. There's another one just a little bit north off the coast of BC, just next to Haida Gwaii, Queen Charlotte Islands. Another transform boundary here. And if I go back even further, we look at the giant map again. You can see right through the middle of California down through Baja, Mexico, you end up with this big transform boundary on land. Now, if you fall between the plates, that implies that there's somewhere to fall. You can literally go and stand on this transform boundary in the San Andreas Fault. You could stand out. You could put 1 foot on one side, 1 foot on the other. Remember, these are two continental plates. They're kilometers thick, and they are butted up right next to each other, and they're really, really pushing into each other really, really hard. So it'd be like you stepping between my hands right now. You wouldn't just fall between them. The pressure that's built up between these things is absolutely immense. Even though one's going one way and the other's going the other way, if they were far apart, they would just move past each other and we wouldn't end up with any earthquakes. They would just be like, oh, this is great. We can just move past each other. But they're being pushed into each other really hard, and they slip and slip and slip. Even if you went to the Rift Valley in Iceland, where those two plates are moving apart because of divergence, you can stand between them and nothing happens to them. So do I think Superman could? I don't know the limits of Superman's power, but I would assume that he probably couldn't. I don't know. Although he spun around Earth the wrong way to make it go back, maybe he can. I'm not sure. You'd probably have to ask an expert on it. All right, So back to the idea of symbols. You guys, I kid you not, on the provincial exam or test, there'll be questions that say, you know, is an earthquake likely to happen? Not an earthquake, that's a bad example. Is a volcano likely to happen in California? So you go to California and you go, okay, here's California. And oh, that's a transform boundary. So you can see the transform fault here. And do you think an earth or a volcano will form there? Well, no, there's nowhere for the magma to rise up. So they ask questions like that. You need to be able to use the information here on your map to identify the type of boundary, divergent, convergent, transform, and identify things that are happening as a result of it. If you have subduction happening, like off the coast of South America, here's a great example of the Nazca Plate getting subducted under the South America Plate. You get this subduction happening, this Nazca Plate's going under it. Where you're going to get volcanoes? Yeah, that plate's going to melt, it's going to rise up, you're going to get a big chain of volcanoes. That's the Andes right here. So it's going to ask questions like that. Can you identify what's going on in terms of the map and what happens at those types of boundaries? So that's essentially the tectonic plates stuff. Now, the section in your notes continues on with volcanoes and earthquakes, but I think it's just a lot. So what I've done is I've broken it up into two sections. So 10.2, we have the tectonic plate stuff, and then we're going to talk about volcanoes and earthquakes after. So it is 10 after 10 right now, almost. What I'd like you guys to do is I'm going to give you, let's go with 30 minutes. I'm going to give you guys 30 minutes to go and do the tectonic plates activity from the course. So if you've done it, you can just continue on in the notes or whatever you want. But I'm going to give you guys 30 minutes to go through this activity, plate tectonics. Print it, do it on the computer, I don't care. After that 30 minutes, I'm going to get you guys to come back, and then we're going to talk about earthquakes and volcanoes for a little bit until the end of the block. And then next day, we do have a double block again on Wednesday, but it won't take, pardon me, it won't take us that long to get through it. So we'll get a jump on some of Wednesday's stuff after this like 30-minute break. So does anybody have any questions before we take a bit of a break here? I'll give you guys half an hour to do this plate tectonics thing, grab a snack, drink, whatever, and then we'll, you can draw it by hand in Word. Just grab the little pen and draw it. It doesn't have to be perfect. The plate boundaries, if you have a thick thing and a little thing going underneath it, I don't mind if it's drawn on the computer. It doesn't matter much to me. If you want to print it and do it by hand, great. I'm not saying you have to submit it right now. I'm just giving you time to do it. And then you hand in the plate tectonics assignment, this Word document behind me, with the learning guide at the end of Unit 10, like we've been doing with our assignments. So I get Mr. Ross to put up that 30 minutes. I will see you guys back here in a little while. Thanks. Hi guys, welcome back. If you can fire me off a green check mark, just make sure everything's good, and then we'll just continue on. I see you guys had a few issues and some questions and stuff, so I'll get to those for sure. Just want to make sure everything's good. Perfect. All right, so we're okay. The little error that's coming up is saying, I can't, open this or access this. It's just kind of like one of those things your computer's warning you. It's like a Java thing, and so if you run it, it's not going to install a virus or anything on your computer. The other thing that you could be running into in terms of troubles is where it says click to run, it doesn't work, and then if you click above it, it does work. So that's kind of silly. I don't know why it doesn't work there, but if you click above it, it should run as just fine. So hopefully that gets rid of a few of your questions. Abby asking a question about why the Earth's crust is less dense than the core. Can anybody answer that question? Anybody have any idea? I know, it's kind of weird. I don't know why it's showing up like that, but it is. It is what it is. I'm sorry. Anyone think of something, why does it say tectonic things overdue by 4 days? It could have maybe when I opened it, put in a due date. Just ignore it. I'll go and change it later. I'll put in a due date of Friday for it. You're trying to update your Java? Yeah, I'm sorry. We're going to run into problems like that from time to time. So the more ironies you go further down. Think of maybe getting back to Abby's question. Think about in terms of general just densities. Think about things in your everyday life and their relative densities. So don't think specific to the layers of the Earth. Just think in general. You learned about density in grade 8, I think. What do you guys know about density? It's actually kind of, once you think about the answer, it might be like, oh, really? Yeah, that's exactly it, Ava. If you have something that's less dense, it floats. So if the surface, if the crust was more dense than the core, you would end up with the crust kind of sinking down through the middle of the Earth and kind of settling down in the middle of the core. I know, it's kind of one of these light bulb things. It totally makes sense though, right? So when we think of rock, we just get into this mindset that rock is so hard and it can't move and you can't bend it and things like that. But the Earth has a tremendous amount of energy in it. It can force this rock to melt and fold and bend, and it can actually liquefy it and turn it into a magma. If it makes the surface, it becomes lava. And you end up with this really crazy things that just don't make sense in our everyday lives. Our normal temperatures and pressures on the surface, we can't really fathom with our experience of what is actually happening below the surface, because there's sort of nothing in our everyday makeup that would allow us to kind of, experience what it would be like to be hot enough for rock to melt, or enough energy or force to bend rock, to fold rock. So you end up with these really crazy things. So so hopefully you get the idea there that the continental crust is less dense. It floats kind of on that asthenosphere, the lithosphere, that hard crust, kind of floats up there. So there you go. Just out of curiosity, did you guys have enough time to finish that? Almost finish it? Where are you guys at with that? I'm just trying to plan out today and next day to kind of see what we can cover in terms of material. No, didn't finish it. Okay. So you guys will need some more time for that, which is fine. The next section isn't really its own section. Half left, almost done. Cool. So 30 minutes wasn't quite enough, but you're nearly there. That's all I wanted to know, which is great. Taylor, you're still working on downloading it. Okay. Perfect. I'm going to just mosey on over. The next section isn't really a section. It's just the 10.2 continued. And it's kind of a fun section because everything we talk about in earth science takes really long periods of time. But earthquakes and volcanoes both happen in sort of a human time frame. When you watch a volcano erupt, magma comes flying out and things are happening in kind of a human time scale. So it's really cool. Earthquakes happen in a human time scale. They'll last for, a minute. That's an earthquake. Awesome. You can experience that. Whereas right now I'm standing on the North America plate and it's moving at about 2 centimeters a year. In my lifetime, if I'm lucky enough to live 100 years, it's going to move about 2 meters in my entire life. Nothing really exciting is going to happen. But these things happen in a human time frame, so we can experience them. And I know it sounds silly, but if you've ever experienced an earthquake, it's scary and it's amazing all at the same time. So we're going to talk a little bit about volcanoes and earthquakes. There's a little bit of notes here, but the majority of it is just me blathering on about really cool things that I find really interesting, and I hope you find them interesting as well. So earthquakes are extremely difficult to predict. That is why they're so devastating, and that's why they can cause so much damage. We can't predict very accurately when they're going to happen, how big they're going to be. We give these things time frames. We say, well, the Juan de Fuca plate's being subducted underneath the Pacific plate off of Vancouver Island, and an earthquake hasn't happened there in, this many years. And if we look in the past, in the geological record, we can see that an earthquake happens maybe every 1,000 years. So if we're past 1,000 years since the last earthquake, well, we know we're due for another one. And this is kind of what's happening right now. I don't have the exact dates for our area here, but Vancouver, Pacific Northwest is due for an earthquake. There hasn't been a major earthquake for a long time. So we know that energy is building between the plates, and it's eventually going to slip and let go. And it's just a matter of time before that happens. So we end up with these really long distances, these plates sliding past each other, either going under, sliding next to each other, or into each other. And the energy builds up. You imagine putting really long things together and pushing at them really hard, and they're going to slip eventually. So there's some important vocab you need to learn. Just two things. When you talk about earthquakes, there's two important words. The first word is the focus, and that is exactly in this fault line where the earthquake happens. So this fault is a place between two plates. It's exactly where it happens. Well, we don't live, 100 kilometers or 10 kilometers down in the earth, so we don't really care as much where the focus is. What we're concerned about is where the epicenter is, and the epicenter is the point on Earth's surface directly above the focus. So we're always interested in the closest city to a major earthquake or anything like that. So there you go. The two important words for earthquake are focus and epicenter. We'll look at a few other ones, but they are very similar in their meaning. They're both where the earthquake happened, but where the one on the surface is the epicenter, the one under the surface is the focus. So there you go. That's kind of a boring slide. Apparently I didn't have time to put a picture in this one. Earthquakes happen at different depths. So when you have a plate getting subducted under another plate, you end up with earthquakes, very shallow ones up at the top. You can end up with earthquakes well down into the earth. The shallow earthquakes have a really, their focus is close to the surface, so the energy causes more damage because it doesn't have to travel through as much rock to kind of get dissipated. But if you have a really deep earthquake, then generally speaking, they're not quite as devastating because there's more rock for that energy to kind of get dissipated in. If you think about sound is a transfer of energy. I vibrate the air, it travels to your ears, you hear it, it vibrates your ear. Well, if I'm talking to you from like outside of your front door, well, the door is there and you can't hear me quite as well because the door is kind of muffling that energy that's getting transmitted. Same idea with earthquakes. The deeper the focus, the less energy gets transmitted, gets dissipated through all the rock. Why don't we have global earthquakes, Alex? What do we think? Where do earthquakes happen? Well, earthquakes happen at fault lines between two plates. So when two plates meet, the plates are all going in different directions, different places at different speeds. So you wouldn't end up releasing energy in one spot. And then that, I guess, what I'm kind of implying from your question, or what I think you might be implying, is like an earthquake here causes an earthquake somewhere else, causes an earthquake somewhere else. There's just not enough energy released for it to travel far enough to hit another fault line, I guess might answer your question, or it might not. So subduction zones because of the way the plates interact, you have shallow earthquakes, you can have really deep earthquakes. The volcanic hotspots, which we haven't talked about yet, but they can produce earthquakes as well because that magma pushing up. It might be theoretically possible, I'm not sure. I'm thinking the amount of energy released from an earthquake might not be enough, but it could happen, I'm not sure. What does happen along a single fault line is you can get a big earthquake in one spot, and it can release tiny little earthquakes all the way along the fault line. So a common one that just happened was the Japanese earthquake about 10 years ago or so. We talked about Japan moving, like 2 meters closer to North America. So normally plates move 2 centimeters. It moved 2 meters in a second, instead of moving 1 centimeter or 2 centimeters in a year. So this is the type of energy that's being released when these plates build, and they slip, and Japan moved closer to North America by about 2 meters. Could nuclear explosions cause earthquake? Nuclear explosions are pretty small relatively compared to the energy released in an earthquake. Earthquakes release thousands of nuclear explosions worth of energy. These are the types of forces it's just almost unfathomable how big the energy is released in an earthquake is. Nuclear explosions are small compared to them, if you think about it that way. There's one exception, or a couple exceptions. We'll talk about them later on. All right, so here's a map, and I haven't drawn plate boundaries on here with these red dots or anything, and the legend's really hard to read, but it doesn't really matter. What you need to know is that this map is showing the depth of earthquakes. So red dots are very shallow earthquakes, and then let me get my color straight here, yellow are deeper, green are deeper, and blue are the deepest. So the focus is the deeper, so red is very shallow. So if we took a map of the Earth and we measured every single focus and we put its depth, this is what this map is showing. Now, you can see that earthquakes happen at the fault lines where the plates meet. So you notice down the mid-Atlantic rift here, you end up with all of these shallow earthquakes. Why don't you have deep earthquakes at a rift valley? Let's see if we can put some ideas together here. Why are there no blue dots here? Why are there no green dots here? Why do we only have red dots? And then our little neck of the woods here, we have red dots again. Red dots here, red dots here. The crust very thin, that's right. Generally speaking, the earthquakes are pretty shallow in the Vancouver area. The crust is thin. You have these two plates moving apart, right? So the magma is rising up between them, causes lots of small earthquakes, but there's no subduction happening there to cause really deep earthquakes. If we think about, subduction, you're going to get a plate going under, you're going to have earthquakes happening way down here, really deep foci? I don't know if that's plural or singular, I'm not sure. Doesn't sound right. So you go here, where this Nazca plate is going under the South America plate, and you end up with these really deep earthquakes that are further inland. And then look over here, you end up with extremely deep earthquakes where you have subduction happening. This is New Zealand area here. So this is kind of what's happening. This is an example of subduction where these earthquakes are occurring. So you have this is Nazca, so that's what we're just looking off the coast of South America, the Andes Mountains there. You have these really shallow earthquakes happening right here, and then you have your mid-range earthquakes here, and then you have these green guys. And then the blue ones are these really, really deep earthquakes that have really deep focus. and very relatively small amounts of damage. But look at how far inland we are here. This is 1,000, that's 500 kilometers right here, 1,000 kilometers. So we're only a couple hundred kilometers from the ocean, our plate. So we're talking about like earthquakes that would happen in maybe 1,000 kilometers. We'd be looking close to the edge of Alberta maybe. The Pacific plate is kind of riding on top of that other plate. So you can end up with earthquakes happening thousands of kilometers from the actual subduction zone, the actual trench that gets formed because of those plates getting slid under one another. So you can see the majority happen kind of in this area here. Very few deep earthquakes, but they do happen. All right. This is the notes just mention hotspot, but I think it's really cool. There's some really cool examples, so I'm going to talk about it for a minute. It's not a huge part of the course, but I find it interesting. So here we go. Abby, you were asking about this earlier. You said, is Hawaii an example of like convergent plate boundary or whatever? But if you look at Hawaii, it's right in the middle of this Pacific plate. So you end up with Hawaii, this hotspot, right in the middle of the plate. Another thing that comes up from time to time is the Ring of Fire. So the most seismically active and volcanically active region on Earth is this circle around the Pacific plate. The Pacific plate's kind of pushing into all the plates around it, and you end up with like Japan down through Philippines area, Indonesia, down New Zealand, and then up the Andes here, up North America. So you have a big ring, and this is where the majority of Earth's volcanoes are, the Ring of Fire. And we're actually on the Ring of Fire. So you think, oh, Kelowna, there's no volcanoes near us. Yeah, there's a few, a little bit closer to the coast, but we're going to talk about those here in a second. So what happens in a hotspot is you get magma rising up through a really strong plume of magma. And we talk about the mid-Atlantic rift here is a really big plume that kind of rises up for a really long distance. A hotspot is a really isolated area where magma rises up and it tries to break through the surface. And every once in a while, it does break through the surface. So here's how sort of Hawaii was formed. Get out of the way here. There's a big hotspot underneath Hawaii, and this plate is kind of sliding along. So these islands are being formed as the plate, you can see the direction here, this plate's kind of sliding along the hotspot. So if we can go down a little bit there, Mr. Ross, below. Thank you. Here's an example. I know this isn't like Russian or something, but it's a good example. So these islands over here, about 5.6 million years, 4.9, 3.4. So Oahu is kind of where the capital and everything is. Molokai, Maui, Hawaii. And the most recent one here is Lohi, which is the next Hawaiian island that's forming right now. Soon it'll break the surface and you'll have the next Hawaiian island forming. So this is kind of the most counterintuitive idea there is. The biggest Hawaiian island is Hawaii, and then they generally get smaller as you get older. So I'll ask you this question. If the biggest island is the youngest, why are the Hawaiian islands getting smaller as you move away from that hotspot? Why isn't the oldest island the biggest? If the new island of Hawaii is still being formed right now, why is it's getting bigger? Why aren't the older islands bigger? Does it make sense that the oldest island would actually be the smallest? They're not actually technically going underwater, though the sea level isn't really, well, I mean, it is rising a little bit, but it's not enough. But you're on the right track. It has to do with water. So Hawaii is the biggest, but it's also the youngest. And then soon, Lohi will break the surface and it'll be the youngest, and it'll get bigger and bigger and bigger. Why are the older islands, why are they smaller? We think. Has to do with water? That was a good hint, I thought. I thought that was a great hint. the hotspot's stationary, the plate's kind of moving across it. So as the hotspot rises up, it kind of breaks through, makes an island. The island gets formed, and then it breaks through again. Hawaii is still growing. That's why it is the biggest. But why is the oldest the smallest? Come on, somebody's got to put it together. Nobody? All right, I'll give you guys a second. I'm not going to give it up that easy. Let's look at Google Earth. I love Google Earth. Let's look at Hawaii from space, shall we? All right, I'll just stop it there. So you can see this plate's moving this direction, and maybe I shouldn't put Hawaii directly behind my head here. So this is the island of Hawaii, and then Oahu down here, and then Lohi's starting to form right here. You can see this chain. Why are these aren't above the surface anymore? Why are they under the water? This chain, you can see the hot spot kind of moves along here. You can clearly see from space that there's all these islands. Why are these ones underwater now? Why are they no longer above water? Come on, somebody, anybody. Nobody? Am I gonna have to just give you the answer? I feel like I'm cheating you guys if I have to just tell you what it is. I've actually seen this question on provincial exams before as well, so it's an important idea. The water overtook them. You're there, I think you know what you're talking about, but that's not exactly what I'm hoping for. The idea is that the older, remember when we talk about an island being formed, like Hawaii, if I jump around here a little bit, we're talking that this Hawaiian island where you can go right now is 700,000 years-ish old. If we go back here, we're talking Oahu's 3.4 million, and then Kauai is 4.9 to 5.6. We talk about these really immense time frames. What happens to rock over millions of years? Well, if you're in the middle of an ocean, you have waves crashing on your shore constantly. You have constant rain pouring down. So the older the island, the more erosion that's occurred. Because you have erosion happening for millions of years, the islands that used to break through the surface, they were there, they were big islands. And then the waves break them down, they get smaller and smaller and smaller until they go under the surface. So the biggest island is the youngest because it hasn't had very long to erode yet. It is currently being built. The magma rises to the surface, becomes lava, forms the island, it gets bigger and bigger and bigger. And then that plate moves over a little bit, and then you get the next breakthrough occurs, and that's slowly moving, and it's going to get eroded, and then the new island gets formed, and then you end up with erosion happening over millions of years. So that's a really cool example of a hotspot that's underwater, in the middle of that Pacific plate. Let's look at a hotspot that happens under the ground. This is called Craters of the Moon National Park. It's in Idaho. Has anyone ever been here before? I'll just pause this for a second. Anyone been to Idaho before? Here's Idaho. Here we are up here in the Okanagan Valley. There's Kelowna. And then we jump down into Idaho here. No one's been to Idaho before? Mr. Ross has been to Idaho. Have you been to Craters of the Moon National Park before, Mr. Ross? No. All right. I was lucky enough, my wife and I drove out to Ontario a few years ago, and we went through the States and we went down through here. It was a really cool trip. My mom had actually been to this place before me, and she said, you gotta go here, it's a really cool spot. So this is Idaho. It's kind of, sort of, yeah, it's a lot of power to wield. You're right, Alex. This is the middle of Idaho, and you can see there's some mountains up here, and then it's kind of like a plains sort of area. And you can see this kind of stain on the surface here of Idaho. And if I go a little bit closer, it's black, which is kind of weird. There's not really much happening. There's no volcanoes to speak of here. But if you go in even closer, and you can see there's another spot down below here, this is called Craters of the Moon National Park. It's in Idaho. And these are all really big lava fields. You can kind of see it in the image here. These huge fields of lava, absolutely huge distances. I mean, hundreds of kilometers. You can see it looks like another sort of, I don't know, planet, I guess. There's these cool tunnels, and I'm going to just zoom in a little bit closer here, see if I can get some other pictures for you guys. Pictures aren't loading. No, don't want that one. Don't want that one. Yeah, I guess that's as good as we're going to get. Anyways, it is lava fields, and it looks like a moonscape. There's absolutely nothing there. There's sort of, you can see the lava. This is what we call primary succession, kind of trying to take over again. But you end up with these immense fields of lava. They're all dried up. This is where you can actually go out, and there's some mountains, like old cinder cones that you can climb, and some really cool stuff. You can see it's lava, like lava that's dried, all over the place. So if I just zoom out, obviously there is some sort of a hotspot that was there at one time. And you can see this big lava field. I mean, this is most of Idaho, and it's a really cool spot if you ever get a chance to go there. But Mr. Borden, what are you going on about? Well, the hotspot used to exist under here, but it's not there anymore because that plate's moving. So can anyone think of an area that's close to Idaho where a hotspot might be significant? If I take a little trip here, does anybody know what this area is called right here? Anybody been to Yellowstone National Park? Now, most students know about this because there's kind of a couple of famous Hollywood movies about it, about Yellowstone. Do you think the government hides their secret bases from Google? I have no idea. I'm not kind of skeptical of that sort of thing. So anyways, if you've ever heard of Yellowstone National Park, it is a significant place because there's really cool stuff happening at Yellowstone. Have you ever heard of Old Faithful? It's a geyser that kind of sprays water I forget what it is, it's like every hour and a half or something like that. It's a seismically active area. So the hotspot that used to be under Idaho is still there, but now the plate is moved and it's under Yellowstone. So if you ever get a chance to go to Yellowstone National Park, you should definitely go. See if I can find some cool stuff here in Yellowstone. Let's see if I can find So you can see like this geyser. Basically the water sort of goes under the ground and it gets heated up and kind of gets blasted out. You can see these bison here with steam rising in the background. It's a really, really cool place. There's lots of really cool, documentaries about Yellowstone. It's so seismically active. There's all these hot springs and things. It has its own sort of unique ecosystem. There's some other pretty cool, you can see all the steam rising up when it gets cold out. Really cool sort of pools that are so hot that you can't go in them, you just die. Geysers, all sorts of really cool stuff happening in Yellowstone National Park. So there is a hotspot. If I zoom out a little bit, the hotspot that's under Yellowstone is called the caldera, and it's about this big. So it takes up a corner of the state here of Wyoming, and it's a pretty interesting place. The reason I bring it up, has anyone seen the movie that I'm referring to? I can't even remember what it's called. Is it like the where Yellowstone supervolcano erupts? Why can't I think of the movie name? I'm usually good with movie names. Anyways, the plates all fall apart. I don't think it's The Day After Tomorrow. They go on the ship, and anyways, that's a movie if you guys have seen it. So this is a map that measures the gravitational field of Earth's surface, and you can see Yellowstone is right here. So normally this should just be kind of greeny blue, but this Yellowstone is pushing up. So there's this super hot spot underneath Yellowstone, and it's pushing up, and basically it doesn't have anywhere to go. It's kind of a really thick continental crust that it's trying to break its way through. Now it gets close to the surface, but there's no magma that's broken through and kind of flowed out, kind of like Idaho, the craters of the moon that I showed you. So it's basically what they call a super volcano. And eventually it will likely erupt, and it is going to be somewhat devastating. There's millions of people that live near it. It'll be a very big explosion when it goes. It's not likely to sort of break through slowly and create a volcano or anything like that. So the map behind me here is shows a map of where the actual caldera is. Old Faithful's famous geyser. You get some small earthquakes because it's pushing up. 1959, 7.5. 75 at 6.1. So we're talking about some pretty big earthquakes. It's kind of under the Yellowstone Lake. It's a pretty cool place. So there's a hot spot under there. It will erupt soon. We don't know when, but it's likely to happen in the next few thousand years. Might be here, we might not, you never know. But usually students ask lots of questions about it because of the movie that I can't think of the name of though. Yeah, I know, they can happen in our lifetime and they can happen not in our lifetime. It's just the time scale is so large when we talk about these geological processes. Seismic waves. We talked a little bit about how we know so much about the center of the Earth, but we've never been there. So this is some of the evidence that we use to kind of make up the ideas of what the core of our Earth is going to look like. So seismology is the study of seismic waves, and these are the waves that are released when earthquakes happen. And you can see here they help us learn about the composition and substances of Earth's interior. So if we have an earthquake happening, the epicenter is the point on the surface where it happens. There's basically two types of waves that an earthquake releases. P waves are called primary waves, and S waves are called secondary waves. Now, they travel at different speeds, and they can go through different substances because they're different types of waves. So if we look at the image here, we know that the outer core of Earth is liquid because the P waves that would normally travel, the S waves that would normally travel through get blocked by it. We know S waves can't travel through liquid. So we know the outer core of our Earth is liquid because when an earthquake happens, you end up with these areas on the far side of the Earth that these S waves don't make it to. So you end up with this big sort of shadow zone. And then we can look at how the P waves bend when they enter the solid inner core. And we can use like computer models, and we can figure out exactly where those lines will end up on the far side of the Earth based on it going through a solid core. So this is how we know about the interior of our Earth, because you end up with these waves that get transferred through it. So the image above me here, I know it wasn't Star Trek. I'll look it up. I'll tell you tomorrow. I'm going to feel silly once I look it up. These are earthquakes seismograph readings. So this line here is really flat, and then you get this small shaking. This is a P wave, or the primary wave. And then you get this big jump, which is the secondary wave. And then you get the earthquake, which actually happens, which is some other waves, L waves and things like that. So when you see an earthquake happening, if you can tell the difference between the first P wave hitting and then the secondary or S wave, you can figure out how far away the earthquake is. And if you can use 3 stations, you can figure out exactly where the focus of the earthquake was. So we're actually going to do that next day. We won't have time today. We'll just get as far as we can through this stuff, and then we'll actually do the demo, the earthquake lab together next day. We'll do it together in class. So you need to know the types of earthquake waves. The first one's P wave, primary wave. The second one is an S wave, a secondary wave. Those ones make sense. And then the third one is L waves, or surface waves. And these were actually named after scientists, and their L waves are love waves because his last name was Love. So that's why they're called L waves. So the P wave's kind of like a small shaking, and then an S wave's like a bigger shaking, and then the L wave is kind of like the rolling that causes all of the damage. And we'll look at a few videos and things like that. So I don't know if you've probably experienced this. If you were to go outside, maybe you've seen fireworks happen before, And the first one goes up, and then you see this bright flash of light, and then you hear the big boom afterwards, or lightning storms. If you've ever counted in a lightning storm, was it supervolcano? It could have been. In a lightning storm, you see a flash of light, and then you count 1 Mississippi, 2, to figure out how far away the lightning bolt was to your house, or where you're standing. That's the same idea as with earthquakes between the primary wave and the secondary wave. If we can figure out exactly the distance between those things, we can figure out how far it was away from that point. And we can use something called triangulation to figure out exactly where it happened. So that's what we do, that's how we study, that's how we find out where earthquakes epicenters were, the distance between the P wave and the S wave. All right, so these are the 3 types of waves. P wave is primary wave, and it is a compressional wave. It goes like this. And sound is a compressional wave as well, so P waves and sound waves are very similar. And then you have your secondary wave, which is a transverse wave. Now, the easiest way to talk about transverse waves is if you've ever been to a stadium before, and people in the audience do the wave where it goes around, and then it comes back to you, and you stand up and you do the wave. That's a great example of a transverse wave. Now, the reason a transverse wave is special is because if you think about when I am in a stadium and I stand up and do the wave, I raise my arms up. But which way is the wave traveling? The wave's traveling around the stadium. It gets back to me, I raise my arms up. So my motion is up, but the wave's actually traveling past me. So that's a good way to think of a transverse wave. So compressional waves go in and out. Transverse waves go up and down, but they're actually traveling that direction or that direction, which doesn't make sense. And then you have the L wave, which is a surface wave, which is this rolling that you end up with. And the L wave is the one that causes the most damage. Now, Taylor, you'd mentioned that there was an earthquake in the Lower Mainland not too long ago, which you felt, and they do happen from time to time. I've only experienced sort of one earthquake that I can recall that was strong enough for me to notice. And it happened when I was in high school, so I would have been in grade 11. And I was at the old Kelowna Secondary School on Richter before it burnt down and they tore it down. It's kind of on the corner of Richter and the highway. And I was on the second floor, and underneath was kind of like place to lock up your bikes. So there's kind of pillars that we were kind of up in the air above. Anyways, we're sitting there in social studies class, which was kind of cool. And we had an overhead projector with a screen, and the screen started to rattle. That was the P wave coming. It was like, and we're like, whoa, that's really weird. And I kid you not, the P wave happened, the earthquake happened in Seattle, so it was a long ways away from us, but we still felt it. I looked outside of the window, and as I was looking out, I was looking towards Knox Mountain, so you can imagine looking at Knox Mountain. Now, the P wave hit, the shaking, and the S wave came next, which was just more shaking. And then when that L wave came, was like a rolling of the surface, I could look out of the window and I saw Knox Mountain, and then I didn't see Knox Mountain, and then I saw Knox Mountain, and then I didn't see Knox Mountain. And the whole building was just rolling on these L waves. And it was like being on a boat where you can see the horizon, then it kind of goes out of view, and then you can't see it, then you can see it. And it was a really kind of surreal experience. Made my stomach really upset, kind of like feeling like on a roller coaster. And it was just kind of really weird. Now, it wasn't a strong earthquake, but we were just close enough that we could feel it. And it was a weird feeling. So if you've ever had a chance to experience something like that, it's kind of scary. Hopefully you're not close to the epicenter, but you end up with, the actual ground will roll. That is the amount of energy we're talking about here in earthquakes. Just regular ground rolls. We can't fathom how much energy is in these things. So P wave primary, S wave secondary, L wave is the love wave, or kind of the rolling waves. We'll watch these 2 videos and then we will call her a day. So this is just showing the difference between the waves. Let's see if we can get into this without an advertisement.
Longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
All right, so pretty basic explanation of the two types of waves. Compressional wave goes in and out. Transverse wave, I go up, the wave goes along and then comes back. There you go. This one I love because people that don't understand science think they come up with these crazy kind of theories and things like that. And this is a beautiful example of it. So people say, oh, animals can sense an earthquake before it happens. And fair enough, maybe they can, but I'm gonna kind of try to argue against that. So if you watch this video, it's a dog before an earthquake happens. Here's the dog here, and then you see the dog take off, and then the guy behind this post says, "What's going on, dog?" And then an earthquake happens. So somebody who doesn't really know a lot about science would say, hey, that dog sensed the earthquake before it came. I mean, it wasn't a long time before it happened, but he did sense it. So you see the dog sitting there, looks at the ground, and then he takes off. And then the guy's like, "Where are you going, dog? Come back." And then boom, earthquake. All right. Remember how I told you that the P wave, the primary wave, is a compressional wave. It goes like this. It also happens that sound is a compressional wave as well. So what is actually happening here is dogs have different abilities to hear different frequencies than we do. As that compressional wave was moving through the ground, it actually entered the atmosphere and became a sound wave. So if you watch the dog really closely, you'll notice the dog tilts its head a little bit and looks at the ground. So he can actually, yeah, exactly like a dog whistle, same deal. The dog hears the earthquake right there because it's coming. The wave traveling a little bit faster in the air, and then you get the actual earthquake happening. So when people say, oh, animals can sense earthquakes before they come, well, I guess we could sense a sound. That's one of my senses. They just heard it. That's all they did. I mean, there's probably evidence to say that they can actually physically sense them or whatever. I don't know, that they have some magical sixth sense. But it actually is likely just the dog hearing or an animal hearing the wave before it came. So again, if we talk about the waves that are happening here, this video is a bit difficult, but if you watch it, it's always pretty standard. You can see everything starts shaking, and then it stops, and then there's the S wave happening, and then you get some serious shaking happening. So you get the P wave, you get a little bit of vibration, and then it kind of dies for a second, and then you get the big S wave, and then the L wave kicks in, and everything starts going crazy. Any earthquake video you ever watch, they'll always play out the same way, where you have everything just kind of vibrates. That's, letting people know that the earthquake's going to happen, and then you get the big S wave and the L wave where everything kind of just falls apart. And it's pretty cool. There's literally thousands and thousands of videos online, CTV or CCTV, like security cameras and things that film earthquakes. But if you watch them, you can watch for the P wave to come. You can watch for the S wave to come, and then everything just lets go once that S wave and L wave comes. And they always happen the same way. The closer you are to the epicenter, the less distinction there's going to be between the P and the S and the L. The further you are away, it's very distinct. You have the primary wave, just some rattling, and then you get the S wave where things start to shake really big, and then the L wave, things just kind of fall apart. Really big earthquakes will happen for minutes, not seconds. So Taylor, you're talking about the one that you experienced was like 5 seconds. That's really short. If you were in Japan when that big one happened, the ground shook, like really shook for minutes. And then you get aftershocks, which do the same thing again and again after the initial earthquakes happened. That the plates will, if you have a subduction, the plates will slide, and then it gets stuck again, and then the energy builds, and then slides again, and slides again, slides again, slides again, until it kind of falls into place. So earthquakes are really devastating and very powerful. And we're going to talk about seismometers. We're going to talk about that earthquake lab that is mentioned in the learning guide. There's actual assignment. We'll talk about that all next day. We'll go through it together as a class and make sure everybody's on track with that. So I'm going to leave you guys there. you should be able to get as much done in the learning guide as you can. If you haven't finished 1 through 3 units, get those done before the break. I'll put a due date of Friday for Unit 10. Hopefully you can get it done by then. If you can't, I'll give you the break, but you should be done Unit 1, 2, and 3 before the break, Unit 10 by the end of the break. So we're starting on chemistry after the break, and you don't want to be doing this stuff while we're in the chemistry unit because chemistry is tricky. I don't think there's a ton of pages left in that learning guide, Abby, in terms of notes. We'll talk about seismographs, we'll talk a bit about volcanoes all next day, and then we'll go through that lab together. So you could probably do most of it in the learning guide. I don't think there's anything in there that's terribly difficult, but just use your best judgment for that. Hopefully you can finish that by Friday. That's the goal. This is the only unit in earth science. We might have time, Anna, at the end of the year. If we haven't run out of time, there's a couple other units. There is a unit on radiation, which is kind of related to earth science. And there's a couple units on weather and energy transfer in the atmosphere. We might not get to them. We might get to them. I'm not sure. So this is kind of it for earth science for now. What would the dog hear? Yeah, you said that. I'm not sure what frequency the wave would kind of transmit at, if it'd be really low or really high. I have no idea. You could maybe look it up. I don't know if there's any research that's been done on that. I'm sure there probably is, but I'm not sure what the dog would hear. But it would be like a constant noise for a couple seconds and then boom, earthquake. So we'll leave it there. I won't see you guys tomorrow, but I will see you on Wednesday. I think there's something going on at the museum today I saw on the calendar. So if you're going down to the museum, that would be awesome. I have class, so I won't be there. But it'd be cool if you could come down and check it out with Mrs. Ward and Wood. And we'll see you guys on Wednesday. Have a good afternoon.